Would you ask Dr. Lane to come back in, please?
Mr. Chairman, before Dr. Lane begins,
Right, sorry. Right, Dr. Lane.
Yes.
Now, before you start, Ms. Grange has been asked to repeat the warning so that people who join us partway through aren't taken by surprise. So off you go.
Yes, thank you, Mr. Chairman. So I need to give a trigger warning about some of the content of this presentation. Included in this presentation are some images and videos of fire scenarios, and also included are some images of Grenfell Tower on the night and when on fire, including some images taken from inside the tower after the fire. So anyone who doesn't want to see those kind of images shouldn't watch this presentation. Okay, thank you very much.
Thank you very much. Yes, Dr. Lane. Well, I think we're ready to continue.
Okay.
If you are, thank you.
Yes. Okay, so for the next hour, I'm going to cover two final subjects. So first, the European Reaction to Fire Test Classification System. So I've explained the 4 European reaction to fire tests. So now I need to explain the classification system which is published to use with them. I will explain how the classification system considers all that data produced from those tests and explains how to use the data to classify construction products. The overarching classification standard for European reaction to fire testing is presented in BSEN 13501-1, the fire classification of construction products and building elements, using test data from reaction to fire tests. The scope of the standard states, this European standard provides the reaction to fire classification procedure for all construction products, including products incorporated within building elements. Products are considered in relation to their end-use application. This document applies to 3 categories, which are treated separately in this European standard. I will focus on construction products only today. I have excerpted some key definitions set out in the standard for substrate, standard substrate, and end-use application. It's important to understand those definitions. Substrate is a product which is used immediately beneath the product about which information is required. The classification standard also communicates something called a standard substrate, a product which is representative of the substrate used in end-use applications. And the end-use application is also given a definition, the real application of a product in relation to all aspects that influence the behaviour of that product under different fire situations. First, in the classification standard, it provides at Table 1 all the different European classes. These are in letter form, unlike the national classes, which are typically numeric in form. For each class, this table states a classification can only be obtained by undertaking the tests or the extended application process required for that particular product. The table lists the specific tests relevant to the particular European class, as presented on the slide now. It provides a narrative explanation of the requirements in the main body of the text in the standard that follows. Table 1 contains 7 material classifications possible, ranging from the highest European Class A1 down to the very lowest European Class F. It lists the combination of specific tests required, and it lists the specific classification criteria required within each test. And you will start to see where all this extensive analysis to form parameters is starting to become relevant. I will now go through each of the European classes, starting with the highest performance, A1. The limits I am about to describe are for homogeneous materials and substantial components of non-homogeneous products. Note that for composite materials, each layer must be tested. Composite materials use the same tests, however, the relevant limits are a little more complicated, depending on where each material sits relative to each other and the thickness of the layers. Evidence of an A2 chord ACM panel has been submitted to this inquiry, and this was considered as a composite, and hence the limits for composites was applied, and I just wanted to make that point clear. No relevant test evidence has been submitted to the inquiry for an insulation material achieving A1 or A2, so I'm actually not clear whether it would be treated as a homogeneous material or whether the foil facing would result in it being considered a composite material. Class A1 requires test data from 2 reaction to fire tests: the gross heat of combustion measured in the bomb calorimeter and the non-combustibility furnace test. On the screen, we have shown the requirements and a reminder of the test apparatus. To be classified as A1, the material must also be tested in the BSEN ISO 1182 furnace and cause a rise in furnace temperature no greater than 30 degrees Celsius. The specimen should not degrade by more than 50% during the test, and there should be no sustained flaming observed on the specimen. Only where a material meets all these criteria can it be classified as A1. There are 2 combinations of tests that can be used to classify a material as Class A2. Remember that a Class A2 material would be considered a material of limited combustibility under Approved Document B, and so would apply to an insulation material. In either combination, the single burning item test is required, and that's the test with a corner specimen shown in the bottom photograph. The material must achieve a fire index growth rate, FIGRA, of less than 120 watts per second in the single burning item test. The flame front must not extend to the edge of the long wing, and the total heat release in the first 600 seconds after the primary burner is ignited must not exceed 7.5 megajoules. In addition to the single burning item test, the material should be tested in the bomb calorimeter or the electric furnace as part of the non-combustibility test. For BSEN ISO 1716, the requirement for Class A2 is that the heat of combustion does not exceed 3 megajoules per kilogram. For the non-combustibility test, the furnace thermocouple temperature must not rise by more than 50 degrees C, and the material specimen must not degrade by more than 50%. And finally, the specimen must not flame more than 20 seconds. It is at the discretion of the sponsor whether they test in accordance with Combination 1 or Combination 2 to demonstrate Class A2. Both are acceptable means under the European classification system. The next European classification is Class B. From European Class B downwards, there is a different set of test combinations required. The non-combustibility test and the bomb calorimeter are no longer used, and the remaining classifications rely on the single burning item test and the single flame source tests only. The next 5 slides highlight the requirements to classify a material as Class B, C, D, E, and down to the lowest classification possible, F. As you'll see, the testing remains much the same, but the requirements when analysing the data recorded in the test become less onerous as the classifications move down to F. A Class B material must achieve a fire growth rate of less than 120 watts per second in the single burning item test. the flame front must not extend to the edge of the long wing, and the total heat release in the first 600 seconds must not exceed 7.5 megajoules. In the single flame source test, a Class B material must have had a 30-second exposure, and the flame must not have spread to the reference line at the end of the test, which is 60 seconds. The material must satisfy the criteria for both the single burning item test and the single flame source test to be classified as Class B. As we move down to a Class C material, you'll notice the testing combination required doesn't change, but as I've highlighted in blue, the fire index growth rate may now go up to 250 watts per second, and the total heat release rate in the first 600 seconds has increased to 15 megajoules, and this is Class C. For Class D, the fire index growth rate, FIGRA, increases to 750 watts per second. Note that the lateral flame spread and total heat release rate are no longer criteria in the classification standard. There is no change in criteria from the single flame source test. The next important change occurs at Class E. Now only a single test, the single flame source test, is required, and the exposure time has decreased to 15 seconds with a 5-second observation period. Class F is applied when a product has no performance criteria. It also applies if a product fails to obtain Class E when tested to the single flame source test. I have summarised the classifications and the tests required to obtain them here for the 7 European classes for reference. Now I need to talk again about little s and little d. The image on the screen now is taken from section 14 from the classification standard. It lists all the possible combinations of European classification as I have just presented. And it shows the sliding scale from A1 down to F. But each of these is further subdivided based on the volume of smoke production and flaming droplets production. Classification S1, S2, S3 for smoke production are deduced from the measuring data obtained in the single burning item test, specifically from the data that produces the smoke growth rate, or SMOGRA. Classifications D0, D1 and D2 for flaming droplets and particles are deduced from observations of flaming droplets and particles in the single flame source test and the single burning item tests. I have set out the limits for all the S's and D's. I'm not going to go through them again now, but it is important to understand that the approved document B cited S3 and D2 only in 2013 and therefore set no limit for smoke production or flaming droplets and particles. A final note regarding classification to the European standards. The classification standard states the field of application of the classification is identical to the field of application resulting from the tests or from the extended application process. If different end-use applications are envisaged for a particular product, this may result in different classifications. In considering substrates and backings which can be applied in practice, the classification specifies standard substrates for use in tests and also gives rules for the field of application of test results obtained using those standard substrates. The use of standard substrates is not mandatory. Instead, the product may also be tested in its end-use conditions with a substrate representative of the end use. When such a representative substrate is used, the test result is limited only to that same substrate in its end-use application. The applicability of test results obtained for products attached to a substrate is limited to the method of attachment used in the test. An extended field of application is the outcome of a process involving the application of defined rules that predict a test result, but based on one or more test results to the same standard. For any product or material, a fire test report and a classification report is required. These photos are taken from the French test reports for Renault. It is not possible to understand the substrate or the full details of the fixing for the system being tested by this visual means only. On screen now is the specific field of application stated in that particular assessment report for the Arconic Renault 55 PE riveted system. It's important to read the specific nature of the field of application. It refers to a system riveted on any metallic substructure, and it makes clear the substrate must be to an A1 or A2 standard with a particular density greater than 700 kilograms per meters cubed. It also specifies a minimum air gap of 50 millimeters. The European classes are also referred to from approved document B. Back to table A6, but this time in the European class part of the table. There are two definitions of non-combustible provided, as you can see highlighted on the screen. The first blue box at A relies on testing and classification, as I've just described. The second option in the lower blue box is by means of specific materials deemed to satisfy the performance. Back up at paragraph A, it states there that non-combustible materials are any material classified as class A1 to the classification standard. The second fire definition provided in approved document B is in table A7. This is a key definition regarding the insulation products. You can see in paragraph A that any material defined as non-combustible will also satisfy the European class for limited combustibility too. Secondly, as marked at point B, a material of limited combustibility is defined as a material or product classified as class A2, S3D2 or better. This relies on the test evidence from the two combinations of testing I explained earlier. However, a material of limited combustibility, which has a European class designation, is also referenced for another part of the external wall. So back again to table A7, up at row 6, marked here. Class 0 materials meeting the provisions in Appendix A, paragraph 13A, state, if a material or the surface of a composite product is one of two performances, again the first being composed throughout of materials of limited combustibility, and that means class A2, S3D2, or better, as I have just described. It's essential to be aware this is not in the insulation row in table A7. But I want to discuss diagram 40 when considering the European classes. Taking Grenfell Tower as the building example, the external surface classification was class B, S3D2 or better for the building, because it had a dimension over 18 metres and it was 1,000 millimetres more from the relevant boundary to adjacent buildings. And this applied to the part of the building over 18 metres. So looking at the yellow box highlighted on the building there on the screen and the reference to class B in the blue box marked on the screen. This meant the composite product used for the external surface needed to have been tested as a minimum to the single burning item test and the single flame source test, exactly as set out on the right-hand side of diagram 40. But if you look at the national and European classes together for the external surface of the building, this means the surface must either be class 0 or class B S3D2. But the issue is, by definition, using European classifications, class 0 can only be achieved via clause 13A, and so must be class A2, S3D2 or better. This is a higher performance standard than set out in diagram 40, which refers to class B. There is therefore a disparity between the national class designation and the European class designation. Finally, when I was explaining the test procedures for the European tests, I referred regularly to various calculations required from the test data. I now want to show briefly their relevance to the European classes. First, for insulation required to achieve class A2, S3D2 or better, Table 1 states data is required from 2 test standards, and the limits from the data recorded in the test is also made clear in the classification standard, and those limits are shown on the screen. It can be also A2 can be obtained using these 2 test standards, and again the limits when using this combination are clearly shown on the screen. The requirement for the external surface was to achieve class B S3D2. And Table 1 of the classification standard again sets out clearly the criteria for the classification standard using the data and calculations from those tests. So for all the possible combinations of European classification and the sliding scale down from A1 to F, the test data and the calculations are clearly set out in the classification standard, and each one has limits set for the relevant European class. The inquiry has made me aware of a study on equivalency regarding the national and European classes. In 2000, Exova Warrington Fire Research issued a report titled Radar 2, Project Correlation of UK Reaction to Fire Classes for Building Products with Euro Classes and Guidance on Revision of Approved Document B. A total of 64 products were tested to the national and European reaction to fire tests across 7 so-called sectors of wood, mineral wool, paints, cellular plastics, wall coverings, boards and sheets, and plastics. The introduction to Part 2 of the report states, the objective of this Part 2 work is to consider how the test results and classifications obtained in the Part 1 report may be compared so that classification transpositions may be identified, and if satisfactory correlations can be established, to propose to DETR how a supplementary guidance document for approved document B may be prepared. When comparing the equivalence of Class 0 and the European classifications, 35 Class 0 products were compared. 4 wood-based, 3 mineral wool insulation products, 6 types of paint, 7 types of cellular plastic insulation product, 6 different wall coverings, 6 board and sheet products, and 3 plastic-based products. I do not understand the purpose of testing 3 mineral wool insulation products, nor the cellular plastic insulation for Class 0, as this was not the relevant performance requirement, as I've stated earlier. The only cladding panel tested was an FR high-pressure decorative laminate panel. On screen now is Table 2, taken from Part 2 of the report. that shows products that were tested and achieved Class 0 and their subsequent European classification. I've taken these results and I've shown them on the screen now. It can be seen that the majority of the Class 0 samples achieved Class B. However, one of the samples was as low as Class E. This was a wood fibre board. The Class C product was an aluminium-faced phenolic foam insulation, and the Class D product was an aluminium-faced PIR insulation. The only panel tested was an FR HPL panel, and it achieved Class B. On screen now, I have excerpted the conclusions of Part 2 of the RADAR report with regards to PIR and phenolic foam insulation. With these products, it was observed that in the single burning item test, the aluminium foil facing was penetrated such that the underlying foam was then available to contribute to the rate of heat release calculations, whereas in the BS476 Part 6, the heat release found in the test was not sufficient to displace the classification away from the UK Class 0. Clearly, the introduction of a simple replacement of the UK Class 0 by Euro Class B requirement in any regulatory procedure would discriminate against products listed on the slide, against the practical experience of their acceptability in the UK market for Class 0 applications. I find the RADAR reports are very detailed and require careful study, but I found this particular paragraph particularly striking. Any reference to Class 0 being equivalent to Euro Class A2 would severely restrict the market choice in terms of materials for specifiers and clients. This applies to virtually all organic containing materials. In Germany and France, the authorities have a single classification. Thus, Euro Class B could be a cross-border compromise, which is supported by the high product density obtained at the Class 0 Euro Class B transposition point. Finally, the European classes were referred to regarding the Grenfell Tower primary refurbishment external wall products. Only one product installed on Grenfell Tower was presented as relying on the European classification system, and this was the Renobond 55 PE panel. Celotex did not test their insulation to the European tests until after the Grenfell Tower fire. On screen now is the BBA Agrement certificate for the Arconic Renobond panels. I have highlighted how the BBA represented the standard sample it relied on with a classification of B S2D0. No field of application information was provided. This concludes my presentation on the European classification and reaction to fire testing methods.
Thank you.
Okay, the last section. This is the final section of my presentation, and it focuses on the subject of cladding systems and not individual products as I have dealt with so far. I explain the fire tests for cladding systems referred to within the approved document B, and these are called British Standard 8414 Parts 1 and 2. I explained the performance criteria given in the BRE report BR135 on the subject of fire performance of external thermal insulation for walls of multi-storey buildings, also referred to within approved document B. This explains the performance criteria to assess the test data from the 8414 tests. As a reminder, paragraph 12.5 of ADB states, the external envelope of a building should not provide a medium for fire spread if it is likely to be a risk to health or safety. the use of combustible materials in the cladding system, and extensive cavities may present such a risk in tall buildings. External walls should either meet the guidance given in paragraphs 12.6 to 12.9 or meet the performance criteria given in the BRE report for cladding systems using full-scale data from British Standard 8414 Parts 1 and 2. So the full-scale data ADB refers to is generated using the 8414 test, and it is then evaluated using the performance criteria and classification method described in the BRE document. First, however, I want to explain the derivation of these tests and their performance criteria. These methods are founded on principles aired since the 1980s. In 1988, Rogowski et al. Undertook experiments at the BRE Cardington laboratory due to the rise in what was then the new technique of the application of thermal insulation on the outside face of buildings. Rogowski stated, "The use of appropriately designed systems, particularly on the walls of high-rise buildings, provides an attractive method of energy conservation." He stated the need for improved thermal insulation of buildings had led to the introduction of a range of systems originally designed for external application to solid masonry walls, but noted they were now being extended in application by means of installation on the outside of multi-storey developments, done so as not to disturb occupants during the installation. Rogowski, as part of the introduction to the report, identified that control over the external surface of walls of buildings, particularly those of multi-storey flats, was controlled by reference to BS 476, Part 6 and Part 7. However, he advised that this only provided information on the surface fire behaviour, going on to state that the overall fire performance of ventilated cladding systems could only be investigated under actual fire conditions on a full-scale building facade. To identify the design principles affecting the safety of occupants and the probable extent of fire spread, Rogowski of the BRE conducted large-scale tests in a 4-storey experimental building that was 9.2 metres high and 3.7 metres square in plan. On screen now are 3 of the key conclusions made by Rogowski as a result of his large-scale experimental work. To reduce the risk of vertical fire spread in existing and proposed external insulation systems, the following recommendations based on this test programme are proposed to the Department of the Environment. Proposed systems incorporating combustible insulants with sheeted overcladding should be designed to incorporate fire barriers in the ventilated cavity every 2 storeys. Surface protection applied directly to all combustible insulants must be carefully designed and installed around windows and other openings. Timber cladding should continue to be used only in low-rise developments to avoid extensive self-propagating flame spread over the surface. The BRE were at the time an executive agency of the Department of the Environment. 3 years later, in 1991, a fire occurred in an 11-storey tower block called Knowsley Heights in Merseyside. The fire occurred when rubbish was set alight outside the building. The fire spread from the ground floor up the full height of the external wall of the building, and this triggered further work at the BRE undertaken by Dr. Raymond Connolly in 1994. In relation to Knowsley Heights fire, Dr. Connolly states in his 1994 report, which was titled Investigation of the Behaviour of External Cladding Systems and Fire, a report on 10 full-scale fire tests, that the overcladding system involved achieved a Class 0 rating and the insulation was non-combustible. He also stated that one of the reasons for the rapid spread of the fire was an unusual construction detail, which effectively created a flue that travelled up through the height of the building. Dr. Connolly's 1994 report goes on to detail out an experimental investigation into the performance of external cladding systems on exposure to fire. The objective of this particular investigation was to assess the effectiveness of installation of fire barriers in reducing the fire hazard. Non-combustible insulation was used in each test, and 2 types of external overcladding that achieved Class 0, relying on British Standard 476 Part 6 and 7 tests, were installed. The test rig was of a similar scale to Rogowski et al. The overall conclusions formed by Connolly included the need to install fire barriers in external cladding systems with cavities to reduce the potential fire spread. That fire protection solely around the windows was inadequate. That reduction of the width of a cavity reduced the surface spread of flame over the cladding material. Of particular relevance was, he concluded that small-scale reaction to fire properties of the cladding materials did not reflect the fire hazard associated with the full-scale cladding system. He concluded too that the provision and nature of fire barriers and cavity width needed to be considered. Finally, he concluded the clear need for full-scale testing of performance and fire for what he termed rational design of cladding systems. It is important to note that within his overall paper, Connolly highlighted in his discussion for results for surface spread of flame over the facade the following 2 key points. Connolly states, "It is clear that the BS 476 Part 6 and 7 tests do not accurately reflect the fire hazards that may be associated with cladding systems. Reasons may include the fact that the flame movement in a real cladding fire is in the vertical direction as opposed to the horizontal direction in the test. Secondly, he states that it is clear from experimental work undertaken at Cardington that a cladding material achieving a Class 0 rating may suffer extensive surface burning." On the 11th of June 1999, a fatal fire occurred at Garnock Court in Scotland. This fire involved the external wall of the building, as was the case with the Knowlesley Heights fire. On screen now is an excerpt from the parliamentary inquiry into this fire. Firstly, the inquiry references the previous fire at Knowlesley Heights. It then appears to reference the Connolly tests in 1994, as I have just presented. This inquiry then goes on to state, BRE proceeded to develop an appropriate full-scale fire test, known as a test for assessing the performance of external cladding systems. This test was submitted to the DETR in 1996. This test standard, which had been submitted to the DETR prior to the fire, had not been adopted into the approved document B at the time. However, in the Garnock inquiry, DETR themselves stated that going forward, this test will be referenced in approved document B and that it was intended that it become a British standard. The inquiry has disclosed to me one test standard created by the BRE in 1996, titled CR 213/96. The inquiry has also given to me a second test standard created by the BRE in 1998, 1 year before the Garnock fire. This is called Fire Note 3. Neither of these documents were publicly issued by the BRE, and the authors were Morris, Caldwell, Connolly, Smith and Andrews, noting Morris only worked on Fire Note 3. I have compared these 2 BRE documents and there's no material difference between them. However, 1 month following the Garnock Court fire, in 1999, the BRE published another large-scale cladding test document titled Fire Note 9. This should not be confused with Fire Note 3. I have reviewed the test rig in these 3 publications and there is no material difference between them. So I will now only refer to Fire Note 9. But I have compared it right back with Rogowski's work in 1988 and Connolly's work in 1994, as I wanted to understand how Fire Note 9 had been adapted over the years. And I wanted to know if any fundamental issues observed in those founding experiments had been either retained or omitted. Fire Note 9 was written by S. Colwell and D. Smith of the BRE. I have provided in the script to my slide information on the dimensions of the test rig, which were in general the same as Rogowski and Connolly's test rig. The Fire Note 9 rig did contain a wing wall, which I will explain later, whereas Rogowski and Connolly's test rig did not. Importantly, Fire Note 9 does not include windows in the test rig, whereas Rogowski and Connolly did. The proposed crib in Fire Note 9 was very similar to Rogowski and somewhat similar to Dr. Connolly's experiments. Again, an extensive read of these publications is needed. Fire Note 9 contained pass-fail criteria for a proposed full-scale fire test. These were: a fire test would fail if the temperature rise above ambient, 5 metres above the top of the combustion chamber, exceeded 600 degrees Celsius for at least 30 seconds within 15 minutes of the start time. These pass-fail criteria continued into later versions of BR 135, with additional failure criteria introduced in the third version of BR 135. This is important because Fire Note 9 was first referenced in Approved Document B 2000 as an alternative means for complying with the building regulations for external surfaces. This aligns with what DETR had said to the Garnock inquiry. 3 years later, in 2002, Fire Note 9 was converted into a British Standard 8414 Part 1, as shown on the slide here. The Approved Document B was not updated to refer to this British standard at that time. There were minor changes made to the test rig for the publication of the British Standard. These included the main wall width being reduced from 2.8 to 2.6 metres. This British Standard did not contain pass-fail criteria for the fire tests. However, instead, the second edition of BR 135 was published. Again, Approved Document B was not updated to refer to this. This second edition was authored by Brian Martin and Sarah Colwell. Annex A of the second edition contained the performance criteria and classification method of British Standard 8414 Part 1. The performance criteria were unamended when compared with those presented in Fire Note 9. From 2005 onwards, various amended versions of BS 8414 and the classification method publication BR 135 were made, and I have listed them here on this slide. I will now explain both the British Standard Test Method and the BR 135 classification method in the following slides. I will explain the fire test procedure first and then the classification method in the same style as all the other tests I've explained to you today. First, the tests. British Standard 8414 is a two-part British standard. The scope of both is defined as a test method for determining the fire performance characteristics of non-load-bearing external cladding systems when exposed to an external fire under controlled conditions. The fire exposure is representative of an external fire source or a fully developed post-flashover fire in a room, venting through an opening such as a window aperture that exposes the cladding to the effects of external flames or from an external fire source. Part 1, shown on the left image on the screen, is the test method for non-load bearing external cladding systems when applied to the masonry face of a building. So this scope includes rain screen overcladding systems and external wall insulation systems when applied to the face of a building. Part 2 on the right of the screen is the test method for non-load bearing external cladding systems fixed to and supported by a structural steel frame. Its scope includes curtain walling, infill panels and insulated composite panels fixed to and supported by a structural steel frame. So the primary difference between the two standards is the substrate and framework of the final cladding system. The purpose of the test is to evaluate the ability of the system to resist the propagation of the fire upwards or penetration through the system. Part 1 was the relevant standard for Grenfell Tower. BR 135 contains 2 annexes, and each provides performance criteria to be observed and measured during the 8414 tests. Annex A and Annex B address BS 8414 Parts 1 and 2 respectively. Regarding the test rig used in the British Standard test, the test apparatus consists of a combustion chamber in which a fuel source is located at ground level with an opening area of 2 metres by 2 metres. The chamber is positioned such that the fire can project through the opening at the base of the main vertical test wall. There are 2 8-metre high test walls arranged at 90 degrees to represent the inner angle of a corner. The test specimen on the main wall must be a minimum of 2.6 metres wide when measured from the corner and a minimum of 6 metres in height when measured from the top of the combustion chamber. The return wall must be a minimum of 1.5 metres wide and 8 metres in height. British Standard 8414 states that the test specimen shall include all relevant components assembled and installed in accordance with the manufacturer's instructions, where cladding systems are defined as includes sheeting rails, fixings, cavities, insulation and membranes, coatings, flashings or joints. This is provided at note 1 of the definition of external cladding systems. During the test, 2 types of data are recorded: temperature and visual observations of significant events. First, I will explain how temperature is measured. An array of thermocouples are located on the exterior surface of the cladding system at 2.5 metres and 5 metres above the test opening. Thermocouples do not make direct contact with the cladding and are positioned at a distance of 50 millimetres from the surface. Those located at 2.5 metres are considered representative of a level 1. Those located 5 metres above the combustion chamber are considered representative of a level 2. Thermocouples on the main wall are positioned on the centre line of the wall and then at 500 or 1000 millimetres either side of this centre line. This creates an array of 5 thermocouples at level 1 and level 2 on the main wall. Thermocouples on the return wall are positioned at 150, 600 and 1050 millimetres from the junction with the main wall. This creates an array of 3 thermocouples at 2 heights on the return wall. Internal thermocouples are also placed within the cladding system in any combustible layers that are greater than 10 millimetres in thickness or more. These internal thermocouples are positioned at level 2 only. All internal thermocouples are positioned at the midpoint of the layer and temperature measurements taken for the duration of the test, as shown in the image on the right of the screen. In this example on the right-hand side, there is an external thermocouple by the grey layer and 2 additional internal thermocouples, one at the midpoint of the cavity and one at the mid-depth of the insulating material. If the external cladding system does not offer any protection to openings in practice, i.e. there are no cavity barriers around the openings, then the interface between the test specimen and the combustion chamber must also remain unprotected. This is as stated at Note 1 to the definition of external cladding systems in the British Standard. If horizontal and vertical joints are incorporated into the external cladding system, the test specimen shall be representative of these joints. In practice, if the size of panels in their end use are smaller than the area of wall represented by the apparatus, there may be multiple horizontal and vertical joints. On the left-hand image is an elevation of a panel system, and I have overmarked the joints in orange on the right. The fuel source used in the test is a timber crib, comprising alternating layers of softwood sticks. The crib has a plan area of 1.5 by 1 metre and a height of 1 metre. The crib is ignited with strips of fibre board soaked in white spirit and is designed to represent a nominal total heat output of 4,500 megajoules with a peak heat release rate of 3 megawatts. To give that size some context, in the Eurocode 1 action on structures, the typical residential apartment is assumed to contain a fire load density of 780 megajoules per metre squared. This translates approximately into an area of 5.7 metres squared when fully alight. I have overmarked a 5.7 metre squared area in the drawing of flat 16 on the image on the left of the slide, just to give a sense of scale. Secondly, visual observations of significant events are to be recorded. The standard states, the times of significant events, such as a change of flaming conditions and mechanical behaviour of the cladding systems, are to be recorded, especially detachment of any part of the cladding system, whether flaming or otherwise, or any other fire penetrations through fire stops incorporated within the cladding system. A continuous audio-visual record of the full height of the test face is taken throughout the test to allow for analysis. Cameras should provide coverage of the entire external surface of the material. In addition, internal audio-visual coverage is required for tests to the Part 2 standard to assess any burn through to the internal face of the cladding system. 5 minutes before the crib is ignited, the thermocouples and audio-visual equipment begin taking measurements. The crib is ignited. Temperatures and visual recordings are made from 5 minutes before ignition until 60 minutes after ignition. The crib is allowed to burn for 30 minutes, at which point it is extinguished. The test continues for a further 30 minutes, during which time any observed flaming on the test specimen is allowed to continue burning. The test is stopped early if at any point during the test flames extend above the test apparatus, or if there is a risk to the safety of personnel within the test facility. This stopping of the test aspect was only introduced into the test standards in 2005. It was not cited within Part 1 of British Standard 8414 until 2015, when both Parts 1 and 2 were updated. The reference to this early termination was added to the third edition of BR 135 in 2013, and this is important to note when reading historic test reports. I'm just going to show the video first. In this short video, we see a test being carried out. You can see that the fire in the crib in the combustion chamber has ignited, with flames projecting above the combustion chamber and impacting on the cladding assembly several metres above. The graphs of temperature shown on the right here are measurements taken at level 2, so 5 metres above the opening. These are measured by thermocouples external to the cladding surface, inside the cavity between the cladding and insulation, and within the insulation product itself, and I'll explain this later. A test report should be provided for each test undertaken, including if the test is terminated early, and this is required by the British standard. It should include a full description of the cladding system, together with details of materials and components used, and fixing details, details of the results of the test and observations we discussed earlier, and a record of visual observations made during the test, including flaming and mechanical response, supplemented by suitable photographic records. For test to part 2, full details of the test frame must also be included. It's worth noting that by the time of the Grenfell fire, the BRE were the UK's only testing lab with accreditation to undertake British Standard 8414 testing. Finally, I will summarise the performance criteria and classification methods set out in the classification standard. 3 editions of BR 135 have been published by BRE. The first was Rogowski's work, the second in 2003, and the third in 2013. BR 135 makes clear the application of its classification only applies to the system as tested and detailed in the classification report. When specifying or checking a system, therefore, it is important to check that the classification documents cover the end-use application. BR 135 focuses on 3 main performance criteria: external fire spread, internal fire spread, and mechanical performance. Failure due to external fire spread is deemed to have occurred if the temperature rise above TS, that's the initial ambient temperature before the crib is ignited, of any of the external thermocouples at level 2, and it exceeds 600 degrees Celsius for a period of at least 30 seconds and within 15 minutes of the start time TS. This start time isn't the point at which the crib is ignited. It is defined as the point at which any thermocouple at level 1 equals or exceeds 200 degrees Celsius for a period of 30 seconds. If the temperature of 600 degrees Celsius is not exceeded within 15 minutes, then the system passes the external fire spread performance criteria. To explain the context of this 15-minute window relied upon in the classification method, I have as an example marked up the level 2 external temperature versus time graph taken from a recent MHCLG test report by the Fire Protection Association, and the references are provided here. This was a part 1 test of a HPL panel over a Class A1 insulation material. The grey dashed line, shown on the screen now, indicates 600 degrees above ambient temperature. The blue dashed line indicates 15 minutes after TS. The area in the green box indicates the envelope of time and temperature within the test that BR 135 considers for external fire spread performance. You can see the peak external temperatures in this particular test do not occur in this window and instead occur later at around 30 minutes after TS. Next, failure due to internal fire spread is deemed to have occurred if the temperature rise above TS of any of the internal thermocouples at level 2 exceeds 600 degrees C for a period of at least 30 seconds within 15 minutes of the start time. An example graph taken from BR 135 is shown at figure A6 on the screen now. Please note the clear peak occurring in this graph at 15 minutes after TS. Again, to give some context regarding the 15-minute window relied upon in the BR 135 classification method, I have assessed the level 2 cavity temperature versus time graph from those MHCLG tests again, but considering the measured internal fire spread data. Again, the grey dashed line indicates 600 degrees Celsius above ambient temperature limit, and the dashed blue line indicates 15 minutes after TS limit. You can see in this particular test, the measured peak internal temperatures occurred at around 32 minutes after TS. I decided to take this analysis a little further, and I've analysed 21 BS 8414 test reports. 12 were tested to Part 1 and 9 to Part 2. Of these 21, 7 were the MHCLG tests undertaken after the Grenfell fire, one of which was the HBL test I've referred to already, and the remaining 13 were from tests disclosed to the inquiry by Kingspan, Celotex and Ciderise. On screen now are individual dots representing the peak temperatures measured at level 2 in each of the 21 tests and the time they occurred. I have also coloured the graph to indicate in red what would be considered a failure to meet the current BR135 performance criteria, as shown in the red area there on the left-hand side of the blue dashed line. If one takes the performance criteria as not exceeding 600 degrees C, so the red dashed line, in 30 minutes instead of the current 15 minutes, please note the increased number of failed tests above the dashed red line. The panel should consider if modern materials and modern facades typically reach peak flaming combustion within 15 minutes of the start of a BS 8414 test. But back to the third performance criterion in the BRE classification method, which is mechanical performance. No failure criteria are set in BR135 Annex A for mechanical performance when considering test data from Part 1. Reading from the extract shown on the screen, no failure criteria have been set for mechanical performance. However, ongoing system combustion following extinguishing of the ignition source shall be included in the test and classification report, together with details of any system collapse, spalling, delamination, flaming debris or pool fires. The nature of the mechanical performance should be considered as part of the overall risk assessment when specifying the system. This extract tells us that occurrences of mechanical failure, such as system collapse or delamination, can be recorded in the test report, but do not constitute a failure when classifying in accordance with BR135. And finally, references to this test and classification method during the Grenfell refurbishment. These were referred to as part of the primary refurbishment works. On screen now is the Celotex RS5000 datasheet. I've marked up the sections that refer to British Standard 8414 and BR135. Page 3 of the datasheet provides the following description of the Celotex assembly that was stated as tested and formed part of the classification report. That system was not installed on Grenfell Tower. Just to make a final point, the image on screen now shows the sizes of the small-scale test requirements for the sample sizes to determine material performance as we have discussed today. The final item on the far right is representative of the smallest size flat panel of Renabond 55 PE that Arconic sold as referenced in the BBA Agrement certificate. I have redone that slide, including the 8414 test, which is the very large sample before the Arconic panel. I have also summarised the test duration for each one of the tests I have told you about today. And that ends my explanation of the cladding tests. And I was just going to provide some final points to consider after what has been a very detailed presentation. Throughout this presentation, I have made reference to various issues I thought the panel might like to consider, and I wanted to sum them up now after three hours or so of communicating some very detailed information. That the reaction to fire testing regime is associated with internal room fire phenomena, yet they are relied upon in the statutory guidance document to reduce the surface's susceptibility to ignition from an external source and to reduce the danger from fire spread up the external face of the building. That the national reaction to fire test includes one surface spread of flame test, and this measures spread in the horizontal direction. That the external surface and the insulation have been considered separately for several decades, and that Class Note has been the reference for the external surface performance since 1965. That the definition of Class Note has degraded with time, reduced from non-combustible materials throughout, and also the role of the substrate removed from the statutory guidance document. Yet both the national and European reaction to fire testing regime very carefully set out rules regarding substrates and their impact on fire performance when testing. And that the window of assessment of the data from the large-scale British standard 8414 test is early in the fire and may be before peak temperatures are measured for relevant cladding materials. Overall, though, I hope I have communicated the intricacies of each standard test, the careful explanation provided in each test standard of the physical features of the test rig, how each test rig has been created to represent specific fire performance characteristics, and how specific parameters have been derived for each test, with a requirement then for very careful analysis of the data produced from these tests. Extensive work seems to have gone into defining these tests, how to derive results from them, and how to rely on them to classify construction products and materials. It will be of considerable interest to hear the perspective from those that created and monitored the reaction to fire test standards in this country, those companies that carried out the tests, those companies that issued classification reports, and those companies that issued certificates, their understanding of how those parameters were derived, how those parameters were relied upon, and how relevant they considered them to be to the fire performance of external walls. Thank you.
Well, Dr. Lane, thank you very much indeed. It's very interesting. Not there to digest, though.
No, I know, yes. As requested, yes.
Yes, it's Grange.
Yes, Mr. Chairman. I mean, there's a huge amount of work gone into that to make it quite so clear.
Yes.
So I'd like to extend my thanks, and I'm sure those behind me would as well, to Dr. Lane and her team for putting together such a comprehensive and clear presentation.
Yes, certainly. Well, and we're all very grateful for the enormous amount of work that's been put in, and for a very clear exposition.
Yes, okay, right, thank you.
So we could let Dr. Lane go, can we?
Yes, we say goodbye to Dr. Lane for now. I'm sure she'll be back at some point.
Okay, thank you.
I hope so.
All right, thank you very much indeed, and thank you, Tom, for your assistance.
Yes, and then we start with the first of the Celotex witnesses tomorrow, Mr. Room, who Mr. Millett will be questioning.
Yes, and that's it for today.
That is it for today. We've got an early finish.
Right.
We don't get those very often.
No,
so
we don't.
No.
Good, thank you very much. So it's we'll break there, and we'll resume at 10 o'clock tomorrow when we shall hear from the first of the Celotex witnesses. Yes?
Thank you.
Good.
Yeah.
Thank you very much. 10 o'clock tomorrow, please.